Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we understood the importance of the different coordinate systems while learning this electromagnetic theory. And in that video, we also understood about the cylindrical coordinate system. So similarly, in this video, let us learn about the spherical coordinate system. So first, let us understand what are the coordinates in the spherical coordinate system. So in the spherical coordinate system, we have the three coordinates, that is the r, theta and the phi. So here, if you see this r, then it is the radial distance from the origin. So if you just want to visualize it, then just draw a sphere from the origin. So here, this r represents the radius of this sphere. So here, this r can vary from 0 to infinity. So we can say that the range of this coordinate r is from 0 to infinity. Similarly, the next coordinate is the angle theta. So here, this theta represents the polar angle. So this theta is the angle that is made by this radius with the z-axis. And likewise, this phi is the azimuth angle. So this angle is same as the angle that we have seen in the cylindrical coordinate system. So if we take the projection of this r on the xy plane and draw a line from the origin, then that represents the rho. So this phi is the angle between the rho and the x-axis. So in this way, this theta is the polar angle and the phi is the azimuth angle. So here, this phi is varying in the xy plane, while this theta is varying in this plane. So here, if you see the range of the theta, then it is varying from 0 to pi. So here, when the theta is 0, then the r will be parallel to z-axis. And whenever it is equal to pi, then the r will be in the opposite direction. That means here, the range of the theta is from 0 to pi. Likewise, if you see this azimuth angle, then it is varying from 0 to 2 pi. That means this is the range of the coordinates r, theta and the phi. So in this way, if we have been given some point in the 3D space, then we can find its r, theta and the phi coordinates. That means from the origin, if we draw a line towards the point P, then that radial distance corresponds to r. And if we see the angle between the r and the z, then that corresponds to theta. And from that point P, if we take the projection on the xy plane and connect the intersection point to the origin, then the angle between the x-axis and the rho represents the phi. And in this way, we can find these coordinates r, theta and the phi. So now, let us see, if we have been given this point P in the spherical coordinate system, then how to represent the same point in the Cartesian coordinate system. And then after, we will also see the other way around. So for the spherical to Cartesian conversion, let's say we have some point P in the 3D space and its coordinates are r, theta and the phi. So here, if we take the projection of this radius r on the z-axis, then we will get the z component. So we can say that here the z is equal to r cos theta, right? Similarly, if you see the rho, that is the projection of the r on the xy plane, then that corresponds to r sin theta. So the same thing, if you see in this plane, then you will be able to visualize it better. So here, this z corresponds to r cos theta, while this rho corresponds to r sin theta. And now, if we take the projection of this rho on the x-axis, then we can say that here this x corresponds to rho cos phi. And likewise, if we take the projection of the rho on the y-axis, then we will get the y component, that is equal to rho sin phi. And we already know that this rho is equal to r sin theta. So we can say that here this x is equal to r sin theta cos phi, while the y is equal to r sin theta sin phi. So in this way, we got the coordinates x, y and z in terms of the coordinates r, theta and the phi. So using this expression, we can convert any spherical coordinates into the Cartesian coordinates. So similarly, now let us see the other way around and let us find out, suppose we have been given the coordinates in the Cartesian coordinate system, then how to convert it into the spherical coordinate system. So here, we already know these expressions, right? So here, let us perform the x square plus y square plus z square. So if we do so, then we will get this r square sin square theta sin square phi plus r square sin square theta cos square phi. And for the z square, we will get the r square cos square theta. So in the first two terms if you see, then here this r square sin square theta is common. So if we take it out, then we will have this sin square phi plus cos square phi. And as you know, that is equal to 1. That means we will have this r square sin square theta plus r square cos square theta. So once again, if we take the r square common, then we will have this sin square theta plus cos square theta. And once again, as you know, that is equal to 1. So we can say that this x square plus y square plus z square corresponds to r square. Or we can say that this r is equal to square root of x square plus y square plus z square. So similarly, now let us find the expression of the theta and phi in terms of the x, y and the z. So here, to find the azimuth angle phi, let us take the ratio of the y and the x. So if we take the ratio of y and x, then this r sin theta will get cancelled out from the numerator as well as the denominator. And after that, we will have this sin phi divided by cos phi, and that is equal to tan phi. So we can say that here this phi is equal to tan inverse y divided by x. So in this way, we also got the expression of the phi in terms of the y and the x. So similarly, now let us also find the expression of the theta. So as you can see over here, this z is equal to r cos theta. And the same thing we have also seen earlier. So from this we can say that here this theta is equal to cos inverse z divided by r. And we already know that this r is equal to square root of x square plus y square plus z square. So in this way, we also got the expression of the theta in terms of the x, y and the z. So in this way, we found the relationship between the r theta and the phi in terms of the x, y and the z. That means using these expressions, suppose we have been given a coordinates in the spherical coordinate system, then we can find the equivalent coordinates in the Cartesian coordinate system. And likewise, using this expression, we can find the other way around. So now, similar to the coordinate conversion, let us see the vector conversion. But before that, first let us see the direction of the unit vectors in the spherical coordinate system. So let's say there is some point P in the spherical coordinate system. So if you draw a vector from the origin to this point, then that will represent the position vector. So in general, any vector in the spherical coordinate system can be represented like this. So here, this capital AR, A theta and the A5 are the components of the vector. And likewise, the small AR, A theta and the A5 are the unit vectors in the direction of the R theta and the phi. So as I said in the previous video, the spherical and the cylindrical coordinate systems are the curvilinear coordinate system. That means here, the direction of the unit vector will not remain fixed, and rather, it will change with the position of the vector. So in this case, let us see at the given point what will be the direction of the unit vectors AR, A theta and the A5. So in any curvilinear coordinate system, the direction of the unit vector will always be in the increasing direction of the coordinates. So here also, these unit vectors AR, A theta and the A5 will always point in the increasing direction of this R theta and the phi. So here at the given point if you see, then the R is increasing in this direction. That means here, this will be the direction of the unit vector AR. Likewise, if you see the azimuth angle phi, then it is varying from 0 to 2 pi in the xy plane. That means here at the given point P, the A5 will point in this direction. And likewise, if you see the angle theta, then it is changing in this direction. That means here at the given point P, this A theta will point in the downward direction. So the same thing you will be able to visualize it better if I just take the slice of this sphere. So now, if you see over here, then this is the direction of the AR, A theta and the A5 at the given point. And as you can see over here, all the three unit vectors are perpendicular to each other, or in other words, they are the orthogonal to each other. And since they are the orthogonal, so their dot product will be equal to 0. That means here we can say that this AR dot A theta, AR dot A5 as well as the a theta dot a phi will be equal to 0. And likewise, if we perform the cross product between these unit vectors in the cyclic form, then we will get the another unit vector. For example, here this AR cross A theta will be equal to A5. Likewise, this A theta cross A5 will give us the AR. And likewise, the cross product of the unit vectors A5 and the AR will give us the unit vector A theta. And suppose if we reverse the order of this cross product, then we will get the negative sign before the result. For example, here if we perform the A theta cross AR, then we will get the minus A5. So in this way, here this AR, A theta and the A5 are the unit vectors in the spherical coordinate system. So now, let us see the vector conversion between the spherical and the Cartesian coordinate system. And we will also see the other way around. That means suppose we have been given a vector in the spherical coordinate system, then how to convert it into the Cartesian coordinate system. And then after, we will also see the other way around. So here, like we have done in case of the cylindrical coordinate system, we will derive the transformation matrix, and with the help of it, we can find the vector in the another coordinate system. So here, instead of just writing this transformation matrix, we will also derive it. And as a first step in the derivation, let us find the unit vector conversion between the two coordinate systems. That means here, first we will see that if we have been given a unit vector in the Cartesian coordinate system, then with the help of it, how we can find the unit vectors in the spherical coordinate system. And then after, we will see the other way around. And once we find the relationship between these unit vectors, then with the help of it, we will find the relationship between these coefficients ax, ay, az and the ar, a theta and the a5. So as a first step, let us see the unit vector conversion between the Cartesian and the spherical coordinate system. So to derive these expressions, once again let's say there is some point P in the 3D space. And let's say its coordinates is equal to x, y and the z. So now from the origin, if we draw a vector connecting to this point, then that will represent the position vector. Let's say that is equal to P. So we know that in general in the Cartesian coordinate system, this vector P can be given as this ax times ax plus ay times ay plus az times az. But here, since it is the position vector, so the value of these components ax, ay and az will be same as the coordinate values x, y and the z. That means here in this Cartesian coordinate, this vector P can also be written as this x times ax plus y times ay plus z times az. So here if you see, then our aim is to find this AR, A theta and A5, right? But if you see this expression, then this expression does not contain any variables such as r theta and phi. So here what we will do, we will represent this x, y and z in terms of the r theta and the phi. And for that, we already know this relationship, right? So here specifically we can use this expression because P is the position vector. And due to that, here this x, y and z represents the coordinate values. So basically, here we are applying the coordinate conversion. So after this conversion, this is how the P can be represented. So basically, here we have put the values of x, y and z in terms of the r theta and the phi. So here, if we differentiate this vector P with respect to r, or if we perform the del P divided by del r, then we will get the vector that is increasing in the direction of the r. And if we normalize it, then we will get the unit vector AR. So to find this unit vector AR, first let us perform this del P divided by del r. That means here, we will differentiate this vector P with respect to r. So if we do so, then we will get the sin theta cos phi AX plus sin theta sin phi AY plus cos theta AZ. And if we take its magnitude, then we will get square root of sin square theta cos square phi plus sin square theta sin square phi plus cos square theta. So here in the first two terms, the sin square theta is common. So if we take it outside, then in the bracket we will have the cos square phi plus sin square phi, and we know that that is equal to 1. That means after the further simplification, once again we will have square root of sin square theta plus cos square theta, and once again that is also equal to 1. So we can say that here the unit vector AR can be given by this expression. So similarly, now let us find the unit vector A theta. So this unit vector A theta is equal to del P divided by del theta divided by its magnitude. So here, to perform this del P divided by del theta, we will differentiate this vector P with respect to theta. So if we do so, then we will get this r cos theta cos phi ax plus r cos theta sin phi ay. And for the third term, we will get this minus r sin theta. So similarly, now let us also find its magnitude. So its magnitude can be given as square root of r square cos square theta cos square 5 plus r square cos square theta sin square 5. And likewise for the third term, we will have this r square sin square theta. So once again, here this r square cos square theta is common in the first two terms. So if we take that outside, then in the bracket we will have this cos square 5 plus sin square 5, and we know that that is equal to 1. And once again, these r square sin square theta plus r square cos square theta will become r square. That means the square root of the r square will be equal to r. So in this way, the magnitude of this del P divided by del theta is equal to r. So now, to get this unit vector A theta, we need to divide this expression by the r. That means here, this A theta is equal to cos theta cos phi ax plus cos theta sin phi ay minus sin theta az. So in this way, we also got the expression of the unit vector A theta in terms of the ax, ay and the az. And likewise, now let us also find the unit vector A5. So once again, here this unit vector A5 can be given as this del P divided by del 5 divided by its magnitude. So here, to find this del P divided by del 5, we will differentiate this vector P with respect to phi. And if we do so, then we will get minus r sin theta sin phi times ax plus r sin theta cos phi times ay, because the differentiation of the sin phi is equal to cos phi. And for the third term, as it does not contain any variable phi, so its differentiation with respect to phi will be equal to 0. That means here, this will be the expression of the del P divided by del 5. So similarly, now let us also find its magnitude. So here, the magnitude of this del P divided by del 5 is equal to square root of r square sin square theta times sin square 5 plus r square sin square theta times cos square 5. So once again, in the first two terms, this r square sin square theta is common. So if we take it outside, then in the bracket we will have this sin square 5 plus cos square 5. And once again, that will be equal to 1. That means now we will have the square root of r square sin square theta, and that is equal to r sin theta. So we can say that here this unit vector A5 is equal to del P divided by del 5 divided by r sin theta, and that is equal to minus sin phi times ax plus cos phi times ay. So in this way, we got the expression of the unit vectors AR, A theta and A5 in terms of the unit vectors ax, ay and the az. So similarly, now let us see the other way around and let us find the relationship between this ax, ay and az in terms of the AR, A theta and the A5. So here, since we already know this relationship, so for finding that, we will use the projection method. That means if you see any vector, then it can be represented as the linear combination of the unit vectors AR, A theta and the A5. So here, we can represent this AX like this, because here this AR, A theta and A5 are forming the orthonormal base. That means here, first, these three unit vectors are the orthogonal to each other, and if you see their magnitude, then that is also equal to 1. So because of that, any vector can be represented like this. That is the combination of the AR, A theta and the A5. And here, if you see this CR, C theta and the C5, then they are the projection of the unit vectors AR, A theta and the A5 in the AX direction. That means here, if you see this CR, then that is equal to this AR dot AX. Or in other words, that is equal to AX dot AR. So as you can see, here the dot product of the unit vectors AX and AR represents the projection of the unit vector AR in the X direction. So here, since we already know this relationship, so we can easily find this AX dot AR. And if we perform the dot product of this AX and the AR, then we will get this first term, because the second and the third term will become 0, because as you know, this ax dot ay is 0, and likewise this ax dot az will also become 0. That means this ax dot ar will come out as sin theta cos phi. Likewise, this c theta will be equal to ax dot a theta, and that will come out as this cos theta cos phi. And similarly, this c5 is equal to minus sin phi. So from this we can say that here this unit vector ax is equal to sin theta cos phi times ar plus cos theta cos phi times a theta, and the third term will be equal to minus sin phi times a phi. So in this way we got the expression of the unit vector ax in terms of the ar a theta and the a phi. So similarly, now let us find the unit vectors ay and the az. So similar to the unit vector ax, this ay can also be given as the cr times ar plus c theta times a theta plus c phi times a phi. And once again, here this coefficient cr represents the projection of the unit vector ar in the direction of the ay. That means here this cr is equal to ay dot ar. And here, since we already know this relationship, so we can easily find this ay dot ar. That means here, this ay dot ar will be equal to sin theta sin phi. Likewise, if you see the c theta, then that will be equal to cos theta sin phi. And similarly, this c5 will be equal to ay dot a phi, and that is equal to cos phi. So we can say that this ay is equal to sin theta sin phi times ar plus cos theta sin phi times a theta, and the third term will be equal to cos phi times a phi. So similarly, now let us also find the az. So here, once again this az can be given by this expression, and here this cr will be equal to az dot ar. So here, if we perform this az dot ar with this expression, then we will get this last term, that is equal to cos theta. Likewise, this c theta will be equal to az dot a theta, and in this case it will come out as minus sin theta. And similarly, this c5 is equal to az dot a phi. So in this case that will be equal to 0. That means here this az will be equal to cos theta times ar minus sin theta times a theta. So in this way we got the unit vectors ax, ay and az in terms of the ar, a theta and the a phi. And earlier we already found the spherical coordinate unit vectors in terms of the Cartesian coordinate unit vectors. So now with the help of it we can easily find the relationship between the coefficients of the Cartesian coordinate and the spherical coordinates. And with the help of it we can easily perform the vector conversion. So first, let us see the spherical to Cartesian vector conversion. That means here we already have a vector in the spherical coordinate system. So here what we will do, we will put the values of the ar, a theta and the a phi in the given expression. So here if we put the value of ar, then we will get this term. So again, if you want to follow with me, then you can pause the video and you can check it by yourself. Similarly, if you put the value of a theta, then we will get this second term. And likewise, by putting the value of a5, we will get the third term. So now, in this entire expression, let us combine the terms related to the ax, ay and the az. So now, if we combine the terms related to the ax, then we will get these three terms. Similarly, if we combine the terms related to the ay, then we will get these three terms. And likewise, let us also combine the terms related to the az. So now, if we compare this expression with the general expression of the Cartesian coordinate vector, then here we can say that this term corresponds to ax. Likewise, this ay corresponds to second term and this az corresponds to third term. So from this we can say that here this ax is equal to ar sin theta cos phi plus a theta cos phi, and the third term will be equal to minus a phi times sin phi. And likewise, we can also find the ay and the az. So in this way, we found the components ax, ay and az in terms of the components ar, a theta and the a phi. So here the same thing can also be represented in the matrix form. So this is the transformation matrix for converting any vector from the spherical coordinate system to the Cartesian coordinate system. And in the last video we have seen that if we just take the transpose of this matrix, then we can also find the conversion matrix for the Cartesian to spherical vector conversion. That means here we just need to change the rows into the column. And now this matrix is the transformation matrix for the Cartesian to spherical vector conversion. That means here we just need to remember only one conversion matrix. And with the help of the transpose we can find the another one. So in this way, with the help of this conversion matrix, we can convert the any vector from the Cartesian to the spherical coordinate system as well as from the spherical to the Cartesian coordinate system. But here the only thing is that along with the vector, we also need to know its current position, because we have seen that in case of the spherical as well as the cylindrical coordinate system, these unit vectors are the function of the theta and the phi. And due to that, for the conversion, we also need to know the current position of the vector. So here, now since we know this conversion matrix, so let us see how to convert the vector from the one coordinate system into the another coordinate system. And to understand that, let us take one simple example. So earlier if you recall, then during the derivation, we took the position vector in the Cartesian coordinate system, right? So now, with the help of this conversion matrix, let us find the equivalent vector in the spherical coordinate system. So in general, that can be given as this AR times AR plus A theta times A theta plus A phi times A phi. So basically, with the help of this conversion matrix, we will find the values of this AR, A theta and the A phi. So here, as per this relationship, this AR can be given as this AX sin theta cos phi plus AY sin theta sin phi, and similarly the third term will be equal to AZ cos theta. So here, since the given vector is the position vector, so these components AX, AY and AZ will be same as the X, Y and the Z. And here, now since the X, Y and Z are the coordinates, so we can use the coordinate conversion. That means here, we can represent this X, Y and Z in terms of the R theta and the phi. So as per this relationship, this X is equal to R sin theta cos phi. Likewise, if you see the Y, then that is equal to R sin theta sin phi, and the Z is equal to R cos theta. So once again if you see, then here in the first two terms, this R sin square theta is common. So if we take it outside, then this cos square phi plus sin square phi will become 1. And now this R sin square theta plus R cos square theta will give us the R. That means here, this first term AR is same as the R. That is the radius of the sphere. So similarly, now let us also find this A theta. So as per this expression, this A theta can be given as this AX cos theta cos phi plus AY cos theta sin phi, and the third term will be equal to minus AZ sin theta. So once again, here the value of the AX, AY and AZ will be equal to XY and the Z. And once again, now here let us put the values of the XY and the Z. So if you further simplify it, then in the first two terms, this sin square phi plus cos square phi will become 1. That means we will have this R sin theta cos theta. And if you see the second term, then that is equal to minus R sin theta cos theta. That means these two terms will get cancelled out. And we can say that here this A theta is equal to 0. And similarly, let us also find the A phi. So as per this conversion matrix, this A phi can be given as minus AX times sin phi plus AY times cos phi. So once again, let us put the values of the AX and the AY. So now, if we perform the coordinate conversion, then here this X is equal to R sin theta cos phi, and likewise this Y is equal to R sin theta sin phi. So if you see over here, then these two terms will get cancelled out. So we can say that here this A phi is also equal to 0. So in this way, here this AR is equal to R, while the A theta and the A phi is equal to 0. That means if we see the equivalent vector in the spherical coordinate system, then that will be equal to R times AR. So in this way, With the help of this conversion matrix, we can easily convert any vector that is given to us in the Cartesian coordinate system into the spherical coordinate system. And by taking the transpose of this matrix, we can also perform the other way around. So I hope in this video you understood about the spherical coordinate system and you also understood how to perform the vector conversion between the spherical and the Cartesian coordinate system. So similarly, in the next video, we will see the vector conversion between the spherical and the cylindrical coordinate system. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.